The paper delves into the non-relativistic limit of the Mielke-Baekler gravity theory, focusing on a three-dimensional spacetime. It initiates this exploration by examining the non-relativistic limit of the Mielke-Baekler gravity through a contraction process, which yields a theory that encompasses a source for the spatial component of torsion and curvature. This theory is parameterized by P and Q, two key parameters that play crucial roles in defining the nature of the gravity theory. Subsequently, the authors extend this concept by introducing a Newtonian version of the Mielke-Baekler gravity theory. This version is based on a Newtonian-like algebra that emerges from the non-relativistic limit of an enhanced relativistic algebra. A significant aspect of this theory is that various known non-relativistic and Newtonian gravity theories can be derived by fixing the P, Q parameters, including torsionless models for Q equals 0. This research provides a new perspective on the Mielke-Baekler gravity theory, shedding light on its non-relativistic and Newtonian aspects. By exploring these different facets, the paper contributes to a deeper understanding of the theory's potential applications and limitations, as well as its relationship to other established gravity theories. The Mielke-Baekler (MB) gravity theory is a three-dimensional model that includes curvature and torsion terms, making it a valuable tool for studying the role of these components in the ADS-CFT correspondence. It encompasses various models such as Einstein-Hilbert, teleparallel, and Witten-Lagrangian, with different choices of parameters. The MB gravity has been explored in relation to Chern-Simons, CS, action, black hole solutions, asymptotic symmetries, holography, supersymmetric extension, and its coupling to higher spin gauge fields. Additionally, the paper discusses non-relativistic, NR, symmetries, which have gained interest due to their applications in strongly coupled condensed matter systems and non-relativistic effective field theories. In three spacetime dimensions, NR gravity can be formulated through a CS action under the extended Bargmann algebra, differing from the Galilei algebra by two central charges. This extended Bargmann gravity can be obtained as an NR limit of a U1 enlargement of the Poincaré CS gravity theory. The paper provides a comprehensive overview of the MB gravity and its variants, including its Chern-Simons formulation, U1 enlargements, and non-relativistic versions, highlighting their importance in understanding the interplay between curvature and torsion in three-dimensional gravity models and their implications for quantum gravity and condensed matter physics. In three-dimensional gravity models, the Mielke-Baekler Lagrangian is a prominent example featuring non-vanishing torsion, constructed from the Dreibein one-form EA and the dual-spin connection one-form WA, with four independent constants defining its components. This Lagrangian has been formulated using the Chern-Simons action, providing an alternative gravity description in three dimensions. In the non-relativistic regime, the Mielke-Baekler gravity theory can be generalized by applying a non-relativistic limit to a U1 enlargement of the Mielke-Baekler algebra. This introduces two additional U1 generators, providing central charges that avoid degeneracy. The resulting non-relativistic Mielke-Baekler theory contains sources for both spatial torsion and curvature, dependent on parameters Q and pages. Notably, specific values of these parameters recover known non-relativistic gravity theories. Furthermore, the Newtonian version of the Mielke-Baekler gravity theory can be constructed by extending the Mielke-Baekler algebra in the non-relativistic limit. This yields diverse extended Newtonian gravity theories for particular choices of the P, Q parameters. The Newtonian Mielke-Baekler algebra can be seen as a central extension of the Newtonian symmetry, introduced previously, where an action principle for Newtonian gravity was derived in four spacetime dimensions. The proposed theories have significant implications for future research in non-relativistic gravity models, with potential avenues including the exploration of novel gravity theories and the development of new experimental tests. The application of these theories to real-world systems and the investigation of their cosmological implications also warrant further investigation. The McDowell-Mansouri gravity model, a three-dimensional theory, unifies curvature and torsion in a single Lagrangian, encompassing the Einstein-Hilbert, teleparallel, and Witten's exotic gravity as specific cases. Characterized by constant curvature and constant torsion, the Riemann-Cartan curvature and torsion 2 forms are expressed in terms of their Riemannian and contortion parts. The equations of motion derived from the MB Lagrangian yield field configurations with constant curvature and torsion, describing constant curvature spacetimes with a cosmological constant. This model provides a framework for understanding the interplay between curvature and torsion, offering a more comprehensive description of gravitational phenomena. Notably, the MB gravity model accommodates a range of gravitational theories, allowing for a nuanced exploration of the underlying physics. By reconciling curvature and torsion, the McDowell-Mansouri model offers a promising avenue for advancing our understanding of gravity and its role in the universe. The Chern-Simons formulation of the McDowell-Mansouri model is presented, showcasing the pivotal role of constants sigma I and curvature and torsion parameters p and q. The McDowell-Mansouri algebra, generated by JA and PA, is isomorphic to the ADS algebra with a specific basis, and can be mapped to the ADS algebra through a generator transformation. The gauge connection 1 form A is defined, yielding the curvature 2 form F. An invariant bilinear form is introduced, featuring non-vanishing components essential for the three-dimensional Chern-Simons Lagrangian. This formulation provides a novel perspective on the McDowell-Mansouri model, highlighting its connection to the ADS algebra and the significance of curvature and torsion parameters within the Chern-Simons theory framework. The authors introduce a Chern-Simons theory for the connection A, combining the Einstein-Cartan connection WA, the Vierbein EA, and two U1-form gauge fields Y1 and Y2. This connection is constructed from the Maxwell-Begnado-Steidlboim algebra, including generators for rotations, boosts, translations, local Lorentz transformations, and a U1 gauge symmetry. The CS Lagrangian is derived as a linear combination of 4 terms, each corresponding to a different invariant tensor. It is then shown to be equivalent to the Mielke-Baekler Lagrangian, up to boundary terms, by imposing specific conditions on parameters p, q, and sigma I. The non-relativistic limit is achieved by adding 2 extra U1 gauge fields and introducing new invariant tensors. After taking the speed of light to infinity, a finite and non-degenerate NRCS Lagrangian is obtained. The authors also discuss constructing a Newtonian version by enhancing and enlarging the MB algebra, involving a redefinition of the relativistic algebra and taking the NR limit to obtain the corresponding NR and Newtonian versions of the CS gravity actions. In the enlarged algebra, JA, PA, with 2 additional U1 generators, the non-zero components of the invariant tensor play a crucial role. The relativistic enlarged Chern-Simons CS Lagrangian is constructed, highlighting the significance of extra gauge fields in cancelling divergences. This is essential for maintaining gauge invariance and ensuring a well-defined quantum theory. The focus then shifts to non-relativistic Maxwell-Boltzmann MB gravity, where the non-relativistic version of the MBCS gravity is constructed. This involves a careful decomposition of indices, followed by an Innuigner contraction and scaling, which enables a well-defined non-relativistic limit. The resulting MB algebra consists of spatial translations, spatial rotations, Galilean boosts, time translations, and 2 central charges. These generators form the foundation of non-relativistic MB gravity, providing a novel framework for describing gravitational phenomena in the non-relativistic regime. This construction is significant, as it provides a new avenue for exploring the intersection of gravity and condensed matter physics. The inclusion of central charges, in particular, opens up possibilities for novel gravitational responses and exotic matter couplings. The non-relativistic MB algebra, therefore, offers a rich playground for theoretical explorations and potential experimental discoveries. In the realm of non-relativistic symmetries, the NRMB algebra is examined for different values of p and q. This algebra can be viewed as a central extension of the torsional Galilean ADS algebra, which has implications for our understanding of spacetime and gravity in low-energy regimes. To delve deeper into this concept, the authors construct a Chern-Simons action for the NR algebra. This involves introducing the gauge connection 1 form A and its curvature 2 form F. The components of F are explicitly defined, encompassing various parameters and their derivatives. These components play a crucial role in understanding the geometric structure of spacetime at non-relativistic scales. The section also discusses the non-vanishing components of a non-degenerate invariant tensor, obtained through the contraction process of relativistic invariant tensors. This process is essential for maintaining the symmetry properties of the system under consideration. Furthermore, the rescaling of parameters sigma-1 and sigma-2 is introduced, highlighting their significance in the context of the research. These parameters are critical in adjusting the theory to match experimental observations and theoretical predictions. Overall, this section provides a detailed exploration of the non-relativistic symmetries within the NRMB algebra, shedding light on its potential applications in theoretical physics, particularly in the study of low-energy phenomena. The development of a non-relativistic Chern-Simons gravity theory in 3 dimensions, invariant under the non-relativistic Maxwell-Bargmann algebra, is discussed. This theory generalizes various known non-relativistic gravity theories, including extended Bargmann, extended Newton-Hooke, and non-relativistic torsional gravity. A new invariant bilinear form ensures the non-degeneracy of kinetic terms for each gauge field in the action, leading to well-defined equations of motion derived from the vanishing of curvature 2 forms. The equations of motion involve the spatial torsion and curvature, and the theory's flexibility allows for diverse non-relativistic dynamics with or without non-zero spatial torsion. The development of a novel non-relativistic version of the Maxwell-Bianchi, MB, gravity theory in 3 dimensions is presented, based on an enhanced and enlarged MB algebra. This Newtonian MB symmetry results in a central extension of the Newtonian algebra, underlying the action principle for Newtonian gravity. The enhanced MB algebra introduces 2 additional generators, SAW and LA, satisfying specific commutators with the original MB generators, and is isomorphic to the code-joint adds algebra defined in previous research. By redefining the generators PA and LA, the enhanced MB algebra can be transformed into a new set of generators, which are then used to construct the Newtonian MB symmetry. A connection is explored between the relativistic MB theory and its non-relativistic counterpart, demonstrating that the non-relativistic gravity action can be recovered from the relativistic U(1) enlarged MBCS action by expressing the relativistic gauge fields in terms of the non-relativistic ones and applying a rescaling of the relativistic parameters. The limit xi right pointing arrow infinity is then applied to obtain the non-relativistic CS action. In the context of non-relativistic MB gravity, both torsion and Lorentz curvature are present, measured by parameters q and p, respectively. At the non-relativistic regime, the spatial component of the torsion and curvature behaves similarly to their relativistic counterparts. However, unlike torsional Newton-Cartan gravity, the time component of the torsion remains 0 in this model. The non-relativistic MB gravity action can be derived from the relativistic U(1) enlarged MBCS action, providing a clear connection between the relativistic and non-relativistic versions of the MB gravity theory. This work contributes to the understanding of the relationship between different gravitational theories and the role of torsion and curvature in non-relativistic contexts. The algebra satisfies the code-joint adds commutation relations, defining its structure. This structure is enhanced by introducing additional U(1) generators Y1 and Y2, necessary for the non-degenerate invariant tensor in the non-relativistic limit. The enhancement does not modify the original MB Lagrangian but adds new contributions with parameters beta1 and beta2, crucial for the Newtonian version of the MB gravity theory. The Newtonian MB algebra can be obtained by applying an Innuigner contraction to the relativistic algebra, involving a linear combination of generators through the dimensionless parameter xi. In the limit xi right pointing arrow infinity, the non-relativistic generators satisfy the extended Newtonian algebra's commutation relations. The Newtonian MB, NMB, algebra, a non-relativistic symmetry, is characterized by 2 central charges, z and y. This algebra is distinguished by the presence of these central charges, which are necessary for non-degenerate invariant bilinear traces. Table 2 illustrates different Newtonian-type algebras that can be derived from the NMB algebra, each defined by specific values of parameters, p, q. To construct the Chern-Simons, CS, Lagrangian, and invariant tensor for the NMB algebra must be determined. The equations provided detail the non-vanishing components of this invariant tensor, derived from their relativistic counterparts through the limit xi right pointing arrow infinity and the contraction of generators, as well as the rescaling of relativistic parameters. This process ensures the transition from a relativistic to a non-relativistic context, maintaining the algebra's properties and structure. The mathematical framework of non-relativistic mechanics, NMB, algebra is explored, focusing on the one-form gauge connection and its curvature. The one-form gauge connection, A, is defined as a sum of components including tau h, EAPA, omega j, and others. The curvature 2 form, F, is derived from the gauge connection, expressed in terms of components like r, tau, h, Ra, parent left big eb, parent right big pa, and others. The section highlights the degeneracy of invariant tensor components for the whole NMB algebra and non-degeneracy for the NRMB algebra, emphasizing the importance of considering both sigma, s and beta, s for completeness. The paper presents a novel approach to constructing a Chern-Simons, CS, Lagrangian for the non-relativistic Maxwell-Bopp-Podolsky, NMB, algebra, an extension of the Maxwell-Bopp-Podolsky, MB, algebra. This is achieved by introducing a new curvature tensor, enhancing and enlarging the MB algebra to obtain the NMB algebra. The NMB algebra is then used to construct a non-relativistic CS Lagrangian, which includes terms related to the extended Newtonian Lagrangian, the Newtonian version of the CS gravitational term, and the torsional term of the Newtonian MB gravity theory. The NMB algebra is a non-relativistic version of the MB algebra, constructed by enhancing and enlarging the MB algebra with new generators and structure constants. The authors derive invariant tensors for the NMB algebra, considering two different families of tensors. One obtained when p equals 0 and q equals 2, L, and another when p equals 2, L and q equals 0. Using these invariant tensors, the authors construct a CS Lagrangian for the NMB algebra. This Lagrangian consists of two parts, LNMB, which is the non-relativistic Lagrangian obtained previously, and LNMB, which is a new term derived from the NMB algebra. The LNMB term includes various components, such as the extended Newtonian Lagrangian, the Newtonian version of the CS gravitational term, and the torsional term of the Newtonian MB gravity theory. The field equations for the NMB gravity theory are derived by considering the vanishing of the curvature 2 forms. These equations involve the vanishing of curvature tensors, which are functions of the gauge connection 1 form and the invariant tensors. The paper concludes by noting that the diverse Newtonian gravity Lagrangians known in the literature can be obtained by fixing the p, q parameters as in Table 2. Overall, the paper provides a new perspective on the study of non-relativistic gravity theories and their connections to relativistic counterparts. In the non-relativistic NR regime of the McDowell-Mansouri MB gravity model, an NR limit is applied to the MB algebra, which has been enlarged with two U1 generators. This results in the NR-MB gravity containing sources for both constant torsion and curvature, measured by parameters q and p, respectively. By considering specific values of these parameters, the authors make contact with different NR gravity models defined in 3 spacetime dimensions. The study also extends its results to the Newtonian realm by considering the NR limit to an enhanced MB algebra. Notably, the time component of the torsion remains equal to 0 in both the NR and Newtonian limits for any value of the p, q parameters, which could be related to the torsional Newton-Cartan gravity theory. The exploration of the NR version of an MB gravity model could be further pursued, including supersymmetry and higher spin gauge fields. However, the supersymmetric extension of the MB gravity has been previously explored, but the NR limit of MB supergravity cannot be naively applied due to degeneracy issues. This presents a potential area for future research. In the realm of three-dimensional gravity theories, the non-relativistic NR limit has garnered significant attention due to its potential implications for our understanding of higher spin fields. The paper begins by highlighting the importance of the 2+1 dimensional black hole, which has been extensively studied in conformal field theory and canonical realization of asymptotic symmetries. The authors also draw on previous research into hypersymmetry in d=3, coupled gravity, and massless spin 5/2 systems. They employ the Lie algebra expansion method to derive a non-degenerate NR algebra from a relativistic one, utilizing a particular semigroup S. This approach enables the elucidation of the corresponding supersymmetric extension of the results, potentially leading to the emergence of the extended Bargmann supergravity, extended Newton hook, and the recent NR teleparallel supergravity for specific values of the p, q parameters. In the higher spin case, the authors propose starting with the NR limit of the spin 3 megabytes gravity theory and checking if the spin 3 extended Bargmann gravity emerges as a particular subcase. The paper concludes with a discussion on potential future research directions, including the application of the semigroup expansion method to derive a non-degenerate NR algebra and the exploration of the supersymmetric extension of the results. This study contributes to the ongoing efforts to understand the intricate relationships between higher spin fields and non-relativistic gravity theories, paving the way for further investigations into this complex and fascinating area of theoretical physics. Dynamical symmetries in topological 3D gravity with torsion have been extensively explored in various research papers. Building on P. Baekler et al.'s foundational work on dynamical symmetries, M. Blagojevic and his collaborators have made significant contributions to the field, particularly in the context of 3D gravity with torsion. Their research has led to a deeper understanding of the Chern-Simons gauge theory formulation of this theory. Notably, torsion plays a crucial role in these theories, with far-reaching implications for our comprehension of gravity and spacetime. The incorporation of torsion enables the description of spacetime as a twisted, rather than purely Riemannian, geometric structure. This, in turn, has significant consequences for black hole entropy, asymptotic dynamics, and holography. Several papers have investigated black hole entropy in the context of topological 3D gravity with torsion, revealing intriguing connections between the entropy of black holes and the torsional degrees of freedom. Asymptotic dynamics have also been explored, shedding light on the behavior of gravity at large distances and the role of torsion in this regime. Furthermore, holographic principles have been applied to these theories, providing new insights into the nature of gravity and the structure of spacetime. The significance of torsion in these theories cannot be overstated, as it fundamentally alters our understanding of gravity and spacetime. The research papers discussed here have collectively contributed to a deeper appreciation of the complex interplay between torsion, gravity, and spacetime, paving the way for further investigations into the mysteries of topological 3D gravity with torsion. The AdS-CFT correspondence, a fundamental concept in theoretical physics, has been extensively explored in various research papers, particularly in the context of non-relativistic systems. One notable study investigates the possibility of realizing non-relativistic holography using the Schrödinger invariant theory, which exhibits a non-relativistic conformal symmetry. This approach enables the holographic description of non-relativistic systems, providing a deeper understanding of their behavior. Another research paper explores the application of AdS-CFT correspondence to non-relativistic systems with Lifshitz scaling, which is characterized by anisotropic scaling between space and time. The authors demonstrate that the holographic principle can be used to describe the behavior of these systems, including their thermodynamic and hydrodynamic properties. A separate study focuses on the use of non-relativistic holography to describe the behavior of strongly interacting fermions at finite density. By employing the AdS-CFT correspondence, the researchers develop a holographic model that captures the Fermi-liquid behavior of these systems, providing insights into their low-temperature properties. In addition, the page highlights the importance of understanding the properties of non-relativistic systems, which are ubiquitous in condensed matter physics. The AdS-CFT correspondence provides a powerful tool for studying these systems, enabling the development of novel theoretical models and experimental techniques. The research papers discussed in this context assume that the holographic principle can be applied to non-relativistic systems, which is a significant assumption. Future work involves further exploring the validity of this assumption and addressing the limitations of the current models. In the realm of non-relativistic spacetimes, understanding symmetries and their implications for quantum gravity is crucial. A fundamental concept in condensed matter physics, boundary effective actions for quantum Hall states, serves as a reference point for this exploration. Hörrava-Lifshitz gravity, a theoretical framework attempting to reconcile quantum mechanics and general relativity, is closely tied to holographic duality in condensed matter physics. The authors delve into the concept of scale invariance in both Newton-Cartan and Hörrava-Lifshitz gravity, highlighting its significance in understanding physical systems' behavior across different scales. Chern-Simons theories and three-dimensional Hörrava-Lifshitz gravity are also examined, revealing their relevance to non-relativistic spacetimes. Furthermore, the paper explores Newtonian cosmology, focusing on conformal and projective symmetries within this context. These symmetries are essential for understanding the universe's structure and evolution in a non-relativistic framework. The authors also investigate Newton-Cartan supergravity with torsion and Schr diaresis-Oedinger supergravity, providing valuable insights into the gravitational sector of non-relativistic spacetimes. Finally, the significance of Newton-Cartan gravity and torsion in the context of non-relativistic spacetimes is emphasized, highlighting the importance of these concepts in understanding the behavior of physical systems in these regimes. Newton-Cartan gravity, a theoretical framework that reconciles Newtonian gravity with relativistic principles, has been extensively explored in various research papers. Focusing on its non-relativistic limits and three-dimensional extensions, these studies delve into the realm of torsional Newton-Cartan geometry, three-dimensional non-relativistic supergravity, and exotic Newtonian gravity with a cosmological constant. These novel mathematical frameworks establish connections between Newtonian gravity, cosmology, and quantum mechanics, enabling the derivation of new gravitational actions. Notably, the role of torsion in gravitational theories is a key area of investigation, with significant implications for our understanding of spacetime at very small distances or high energies. The research also ventures into the non-relativistic limits of AD spaces, shedding light on their relation to Chern-Simons gravity. By exploring these connections, the papers provide new insights into the nature of gravity, spacetime, and the interplay between relativistic and non-relativistic regimes. Through these studies, researchers have made significant progress in developing a more comprehensive understanding of gravity, from the large-scale cosmos to the smallest distances and highest energies. The findings have far-reaching implications for our understanding of the universe, and pave the way for further research into the intricacies of gravity and spacetime. The authors present a comprehensive review of the literature on expanded and extended algebras, particularly in the context of three-dimensional supergravity theories. They explore various aspects of algebraic expansions, including non-relativistic spin-3 symmetries in 2+1 dimensions, Wesses-Zumino terms, and generalized Inonu-Wigner contractions. The significance of expanded Lie, super, algebras is highlighted, as they enable the generation of new algebras and superalgebras through abelian semigroups. This approach has been applied to areas such as Chern-Simons supergravity and extended D=3 Bargmann supergravity. The literature review covers the expansion of algebras and superalgebras, with applications to three-dimensional supergravity theories, including extended Lifshitz, Schrödinger, and Newton-Hooke supergravity. It also discusses three-dimensional Maxwellian extended Bargmann supergravity and three-dimensional non-relativistic extended supergravity with a cosmological constant. Additionally, the review includes a discussion on three-dimensional exotic Newtonian supergravity theory with a cosmological constant. This work builds upon previous research on expanded and extended algebras, demonstrating their versatility and applicability in various areas of theoretical physics. The author's review provides a thorough examination of the current state of research in expanded and extended algebras, highlighting connections and relationships between different works in the field. This review serves as a valuable resource for researchers seeking to understand the latest developments and applications of these algebraic structures in theoretical physics.